And what we saw was the performance was quite different in the two regimes. In power limited regime, typically our SNR is much smaller than 1, whereas in the bandwidth limited regime, the SNR is large. And because of this behavior of SNR, what we saw is that the Shannon spectral efficiency in the bandwidth limited regime doubles for if we double our SNR. For every 3 dB increase in SNR, the spectral efficiency increases by a factor of 2. In the bandwidth limited regime, if we have a 3 dB increase in SNR, the spectral efficiency increases by 1 bit per 2 dimension. On the other hand, if we double our bandwidth, then the capacity in bits per second is not affected in the power limited regime. But if we double our bandwidth, then in the bandwidth limited regime, the capacity increases approximately by a factor of 2. And that's really what motivated the name bandwidth limited and power limited regime. If we want a more operational definition, then we said that if rho is less than 2 bits per 2 dimensions, we will have this in bandwidth limited regime. And in this case, rho is greater than 2 bits per 2 dimensions. The number 2 bits per 2 dimensions was chosen because it is like the largest spectral efficiency we can get through binary transmission. If it's an uncoded 2 pm over a channel, then we get 2 bits per 2 dimensions. If we add coding, the only thing we can do is reduce spectral efficiency. So typically, if you're going to operate in power limited regime, the operational meaning is we can get away with binary transmission. In the bandwidth limited regime, we have to resort to non-binary transmission. So in other words, binary modulation is done in power limited regime, whereas we need multi-level modulation in the bandwidth limited regime. The baseline system here is 2 PAM. The uncoded performance was of 2 PAM. In the bandwidth limited regime, it is MPAM. And the way we measure performance in the power limited regime is the probability of bit error as a function of EBNO. Okay. In the bandwidth limited regime, the performance measure is done by probability of error per 2 dimensions as a function of SNR norm. And in this case, we saw that the gap to capacity, or rather, to put it in the other words, the ultimate limit on EBNO is minus 1.59 dB. And here the ultimate limit on SNR norm is 0 dB. Okay. Any questions on this? Yes.
Why do we use EB over not for power limited and SNR norm for bandwidth limited?
That's a good question.
Why do we use EB over not for both regimes?
Why don't we use SNR norm for both regimes?
Yeah.
Now, if we think about the bandwidth limited regime, what we really care about is spectral efficiency, right? What SNR norm does, if you remember the definition, is that it compares the amount of SNR we require for a practical system to that over the best possible system. So in other words, if we do care about spectral efficiency, SNR norm is the right measure to look for. Okay, now what happens in the power limited regime? It turns out probably more for historic reasons, people started with EBNO in the power limited regime. And if you look at the definition of EBNO, it is SNR over rho, right? So in the power limited regime, our rho is small. The SNR is going to be small. But if you look at, because we are in the power limited regime, so we have lots of bandwidth, so our SNR is going to be small and the spectral efficiency is going to be small. But if we look at the ratio between the two, it's going to be greater than minus 1.59 dB. Okay, so it turns out that in the kind of limit we do take, our EBNO remains constant as minus 1.59 dB, and that's probably one of the reasons that motivated to use EBNO in the power limited regime. On the other hand, one could also argue is that what really happens in the power limited regime is our bandwidth becomes really large. So if we say stick with 2 PAM system, right, then we do get a spectral efficiency of 2 bits per 2 dimensions. But that's just because we are using a particular modulation scheme. If our bandwidth is really large, we are not really going to care about what spectral efficiency we use. What really matters is this energy per bit. And that's why this is a reasonable assumption. Does that answer your question? Right, it's not completely clear as to why this EBNO will be is the best here and SNR norm is here if you don't take the limit rho going to 0 here. But again, you can think of it more as a convention. Okay. So if you look in the power limited regime, we are saying rho is less than 2 bits per 2 dimensions. Now, if you use an uncoded 2 PAM, what's your spectral efficiency? It's 2 bits per 2 dimension, right? Now, the idea is suppose we want to design a system with spectral efficiency greater than 2 bits per 2 dimensions. We cannot really use a 2 PAM system, right? Because if we put coding on top of it, all we are going to do is simply reduce the spectral efficiency below 2 bits per 2 dimension. So we have to start with a non-binary modulation, right? So that's how we distinguish between power limited and bandwidth limited.
That's just because you're using 2 PM as a baseline and you're multi-level.
Right. Okay. All right. So let us do an example to finish off this analysis. Now suppose, say you are at a summer project and you are assigned to design some system. Your boss gives you some specifications, like continuous time specifications. In particular, you have a baseband system. The baseband system has a bandwidth of 1 megahertz. You have a power P, which is 1 unit. So that's another resource you have. And if you measure your channel, it can be reasonably approximated as an AWGN channel. So there is no ISI or any filtering going on, just additive wide Gaussian noise. And your noise has a single-sided spectral density of 10 to the minus 6 units per hertz of the bandwidth. And what is your goal? So you have the following goal. Design a 2 PAM system with a specified probability of bit error. And what you want to do is compare this to the ultimate Shannon limit. Okay, so that is your objective. So let us, since we have to compare it with Shannon limit, and we have a direct formula for the Shannon limit, let's just start with that. So for this problem, we have the Shannon limit. You have rho is less than log base 2 of 1 plus SNR. For SNR, I can write in terms of this continuous time parameters. It's P over N naught W. My P is 1 units, N naught is 10 to the minus 6, and my bandwidth W is 1 megahertz here, which is 10 to the 6. So my P over N naught W is basically 1. So I have 1 plus 1, which is 2. This is log base 2 of 2, or it's 1 bit per 2 dimension. So my capacity in bits per second is rho W, and rho is 1 bit per 2 dimension. The bandwidth is 1 megahertz, so I get 10 to the 6 bits per second. So this is my Shannon capacity for this particular AWGN system. Okay. The next thing we want to do is compare this to build a practical system and see how close we get to the Shannon limit. And since you only have to work with 2 PAM, the generic architecture is something we saw last time. You have input bits coming in. Let's call them x sub k, where k is the kth bit. And they belong to a certain constellation. Let's call the constellation points are just, it's a 2 PAM system. So we have minus alpha and alpha. And this goes through a PAM modulator. And one parameter to specify for the PAM modulator is just symbol interval, right? The time between sending consecutive signals over the channel. What you get out is x of t. This is the channel model, n of t. Is additive noise over the channel. And what you get out is y of t. So this is your generic architecture. And now your goal for the design problem is to select alpha and t in the right way so that you satisfy these continuous time constraints, and at the same time you have a probability of error of 10 to the minus 5. Okay? So what would be an obvious choice for t? Right. So, well, the first idea is you are given a certain amount of bandwidth, and you clearly want to send your signals as fast as possible in order to get excellent data rate. Now, because you have a certain amount of bandwidth, what Nyquist criteria tells you is that you want to have 0 ISI. And if you want to have 0 ISI, what you do know is that the symbol interval should be greater than or equal to 1 over 2W. You cannot signal at a rate faster than 1 over t. And so if you look at this, it's 1 over 2 times 10 to the 6. Now, if I do use this particular value of t, then what's my alpha going to be? Well, alpha is simply the energy per symbol. So I know alpha square is the power that I have times the symbol interval t. It's just a definition. This comes from orthonormality of the PAM system that we have. Now p is 1 because that's what I specified in my as a system specification. So this is just t, which is 1 over 2 times 10 to the 6. So I can select this value of alpha and this value of t.
Is it 2pt or is it pt?
Well, alpha square is energy per symbol. So what will that be? What's the energy per symbol if you're sending every t seconds and if you have a power of p? ES that I mentioned last time was energy per 2 dimensions. So in PAM, it will be energy per 2 symbols. In that case, it will be 2pt. Okay, but now if I select these values of alpha and t, will my system work? Is this a reasonable design? Or is there something wrong here? I'm clearly satisfying my
I'm not sure about
the probability of error. Right, exactly. So in fact, I do know how to calculate it, right? What's the probability of bit error? Well, we saw that last time. It was q of root 2 EB over N0. EB is, well, it's same as alpha square because we have 1 bit per symbol. So alpha square is this quantity here, 1 over 2 times 10 to the 6. So this is q of square root of, so 2 alpha square is 10 to the 6, 1 over 10 to the 6. And naught I know is 10 to the minus 6. So this is actually q of 1. And if I do calculate that, it's like 17%, which is nowhere close to 10 to the minus 5. Okay. So any suggestions on how I can improve my system? Increase t, right? What's happening right now is the reason we selected this value of t in the first place is because we wanted to send our signals as fast as possible to avoid ISI. But that's just one of the criteria in my system, right? I have to also satisfy this probability of error criteria. So I want to make sure my probability of error is going to be small. Now, if I look at the expression for probability of error, it doesn't really look at t. All it looks at is this ratio of Ebno, right? So if I want to reduce my probability of error, I have to increase my energy per bit. Now, my energy per bit is p times t. So the only hope of increasing my energy per bit will be to increase t, which means I have to signal at a slower rate. Okay? So we have probability of error. Let's write the calculation down. It's 10 to the minus 5. Last time we saw that the best way to solve this is to look at the waterfall curve, and Ebno in this case is approximately 9.6 dB. I will say that that's approximately 10 on the linear scale. Okay, so this implies that energy per bit is 10 to the minus 5. So energy per bit is p times t in this case is 10 to the minus 5. P is 1, so this implies that t is 10 to the minus 5. So I can send 1 bit every 10 to the minus 5 seconds. So my rate that I achieve, so just write it here, which is 10 to the 5 bits per second. Okay. If you compare this to the Shannon limit, the Shannon limit is right here. You have 10 to the 6 bits per second. So you lose by a factor of 10 in your data rate if you're going to use an uncoded 2 PAM system. So what this example tells you is that if you are going to do more sophisticated coding, you can gain up to a factor of 10 in your data rate. Okay? So if the 10 dB did not really impress you last time, hopefully this example throws more light on the value of coding. Are there any questions on this example?
But since we are signaling at a faster rate now, instead of using sync pulses, we can use something better.
That's a very good point, yes. Well, if you look at the nominal bandwidth here, it's 1 over 2t, right? T is, what, 10 to the minus 5 seconds. So this says 1 over 2 times 10 to the minus 5. So it's going to be 5 times 10 to the 4th, or 50 kilohertz. Okay. The available bandwidth you have, the system bandwidth, if you will, is 1 megahertz. But if you're going to do Nyquist ideal sync pulses, then you only need 50 kilohertz of bandwidth in your system, right? So one advantage of this system, if you will, is that you're not required to do the complicated sync pulses. You do not need to send those pulses. You could simply send, for example, square pulses, and because your bandwidth is such low, you have a very low complexity system. Of course, the price you pay is that you can only send it, you reduce your data rate by a factor of 10. Okay, that's a good point. In fact, there are many points that will come up in this example if you think about it later on. So feel free to ask me questions if you think about some issues later on. Okay, So I think we have motivated the need for coding enough now. So let us look at our encoder design. So a typical encoder design takes bits in. We saw this last time in the context of spectral efficiency, and produces symbols out. So I can represent my bits by, say, a vector b, and I can represent my symbols by a vector x. So every sequence of b bits gets mapped to a sequence of n symbols. Now this output sequence of symbols is not any arbitrary sequence, but it lies in a set of all possible sequences, which I denote by C. And this set is essentially a set of permissible output symbol sequences, which I will write by C sub j, which is a vector in Rn, because there are n symbols being produced. And we can have, say, up to j goes from 1 to m. So we can have up to m symbols. And note that here m has to be equal to 2 to the b in order to be able to map every sequence of b bits to n symbols. So this C is known as a code book, and each C sub j is called a code word. Okay, the standard definition of an encoder. Now in today's lecture and half of next week's lecture, we will be seeing at a very specific case when n equals 1 and 2. In that case, instead of using the letter C, we will be using a different letter A. So C, in that case, we'll call it actually a constellation. So in particular, if n is 1, it's a PAM constellation. If n is 2, it's a QAM constellation. And we'll be denoting it by a letter A instead of C. So A is again a sequence of symbols AJ, which belongs to Rn, where 1 is less than J is less than M. Okay. In this case, A is a constellation. AJs are known as symbols, or sometimes they're also known as signal points in the constellation. Okay. There are a number of definitions that follow from this, number of properties of the constellation rather that follow. So in particular, n is known as the dimension of your constellation. It's the, remember, n is this, and here it's the number of sequences, number of symbol sequences you output for a sequence of b bits that are in. M is the size of your constellation. The energy per constellation is given by 1 over m times the summation of the norm of AJ squares, where J goes from 1 to m. Okay. The minimum distance of your constellation is simply the minimum Euclidean minimum distance between 2 points in the constellation. So you take the norm of AI minus AJ and minimize it over all possible values of I and J. The number of nearest neighbors, or the average number of nearest, K min of A is the average number of nearest neighbors in A. Okay. In addition to this, there are some of the normalized parameters that you saw last time. the spectral efficiency, which is in units of bits per 2 dimensions, is 2b over n. And if we want to eliminate b, we use the relation that b is log m to the base 2 here. And so we have 2 log m to the base 2 over n. Okay. The energy per 2 dimensions, denoted by ES, is simply 2 over n EA. So EA is the energy of your average energy of your constellation. You divide it by the number of dimensions you have to get energy per dimension, and you multiply it by 2. And finally, the energy per bit is ES over rho, or it can also be expressed as EA, which is the energy per symbol over the number of bits per symbol, which is log m to the base 2. It might seem like a lot of definitions, but you will see very soon that they have a very tight interplay among one another, so it's not really as overwhelming as it might seem at the first point.
One question.
Yes.
Why is n is 2 raised to 3?
Because you have 2 raised to b bits coming in, right? Which you map to each.
2 raised to be possible. There are 2 raised to be possible sequences, but all of them needn't be used, right?
Well, we assume that there is no coding going on before the encoder. So you have the source code produces a sequence of IID bits, and then they get mapped to a sequence of symbols. So we allow all possible input bits coming in here, because it's like produced by a source code, like a Huffman code, right? And the idea here is, perhaps what you're asking is, this did not span the entire space of Rn. Like we want to select these sequences carefully here. Maybe we'll come back to that later on in the course. Okay, so let's do an example. So the example is, say you have A, which is a 2 PAM system. And you want to look at this constellation P, which is denoted by A raised to K. The definition of A raised to K is it's a sequence of K symbols where each xi belongs to A. So this is also known as the K-fold Cartesian product of A.
Another question. So it has been pre-decided that B bits will be encoded at a time.
Right. So this is a specific structure we are imposing on the encode. Okay. So this is the constellation, and you want to study the properties for this constellation. For this constellation, what's n going to be? What's the dimension going to be? For B, not A. It's going to be K. Well, the number of points in this constellation, how many points are there? There are K coordinates. Each coordinate can be plus or minus alpha. So we have 2 to the K possible points in this constellation. Okay. What's E of A going to be? K alpha square, right? Basically, we have K coordinates. The energy for each coordinate will simply add up. The energy across each coordinate is always going to be alpha square. So each point in this constellation has an energy of k alpha square. So regardless of how many points we have, the average energy is always going to be k alpha square. Does everybody see this? Oh, you're right. Maybe that was the confusion. That's a good point. Just getting too used to writing E of A. Okay, what's d min of B going to be? You all guys, I think everybody had the right idea. So the minimum distance here is 2 alpha for A. If we look at this point P, we can fix k minus 1 coordinates for 2 points to be the same. They will only differ in 1 point. And so the minimum distance is across that point, which is 2 alpha. What is k min of B going to be? It's going to be k. For each point, let's say the point which has all alphas, we can fix k minus 1 coordinate and find another point which is different in only one of the coordinates, say the first coordinate. We can do it for all k different coordinates. So k min is going to be k for each point, and hence the average number of nearest neighbors is also k. Okay, so now in this case, let's first start with the normalized parameters. It's always good to start with spectral efficiency. That's 2 log m over n. Well, log of m is going to be k, so n is going to be k. So this is going to be 2 bits per 2 dimensions, and this is the same as that of the original constellation A. Your energy per 2 dimensions is going to be 2 over n EB. EB is k alpha square, n equals k, so this is 2 alpha square, and that is the same as the original constellation A. Finally, energy per bit is ES over rho, so it's 2 alpha square over 2, so that's alpha square, and that's same as the 2 PAM constellation. So why did I go through all these calculations? What we see is that the normalized parameters, rho, ES, and EB, are same for the Cartesian product as for the original constellation. And at some level, that should not be too surprising, right? Because what are we doing in this Cartesian product? We are not really doing any coding, right? In this original constellation, we had 1 bit coming in, and we were mapping it to 1 symbol. All we are doing in the Cartesian product is we are taking k bits in and mapping them to k symbols. So we still have 1 bit per symbol. The noise is IID, so it's optimal to do decisions for each of the coordinates independently and decide whether that coordinate corresponds to plus alpha or minus alpha. So in other words, there's nothing gained by doing this Cartesian product. And as you will see, the probability of error expression depends on this normalized parameters, if we want to look at PB of E. And so we do not gain anything in terms of the probability of error versus Ebno trade-off through Cartesian product. So I'm making the note here because that's the only space I have. So the note is, if I look at probability of bit error versus Ebno, the curve we saw last time, it is the same for B and A. Okay? You should be able to convince yourself about this. And so there is really no coding going on here. Okay. Are there any questions on this? Let's look at this problem a bit more carefully now. Right?
What is ES here?
Energy per 2 dimensions. ES will always be energy per 2 dimensions. Throughout the course, we'll be using these notations. EB is the energy per bit, ES is the energy per 2 dimensions. And if you want to say energy per symbol, we'll be using this notation E sub the constellation.
Oh, it's not energy per bit.
No, this is energy, B is my constellation.
Oh, okay.
So that's why it's energy of that constellation. Average energy per symbol in that constellation. Okay, so let us consider the special case when k equals 3. Okay, so in that case, B is AQ. So if I look at all possible points in B, they're going to lie on the vertices of a 3-dimensional cube. Right? That's a Cartesian product in 3 dimensions. Okay, and all my constellation points are basically on the vertices of this cube. The distance here is going to be 2 alpha. That's the length of each edge in my cube. And that's what B is going to be. Clearly, the minimum distance is 2 alpha, as we saw before. Now, let me define a different constellation, B prime. And I'm only going to take 4 vertices from this possible 8 vertices. I'm going to take this vertex here. I'm going to take this vertex here, this one, and this one. I'm only taking 4 vertices. If I want to tell you explicitly what the points are, I need to draw an axis. So I'm simply drawing the x, y, and z axis here. This is x-axis, this is y-axis, and z-axis. And B prime is a subset of the points in this 3-dimensional Cartesian product. They will be alpha, 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 minus alpha, minus alpha, 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 minus alpha, minus alpha, and let's see, so minus alpha, alpha, minus alpha. So 2 of the coordinates will be minus alpha here in these 3 points, and we have 1 coordinate with all alphas. So this is my B prime. What is the minimum distance going to be for B prime? Two root 2 alpha, right? It's basically the length of this edge here. This is 2 alpha, this is 2 alpha, so it's 2 root 2 alpha. So for So in other words, by simply selecting a subset of points, I have been able to increase my minimum distance. Because my minimum distance is larger, I hope that the probability of error will be smaller as opposed to the original constellation. But this comes at a price, right? And what's the price? The spectral efficiency is smaller, right? What if I look at my spectral efficiency? Well, I'm only sending now 2 bits per each point. So 2 bits, each point takes 3 dimensions. So my spectral efficiency is 2 times 2 over 3 bits per 2 dimensions, or it's 4 over 3 bits per 2 dimensions. And this is in contrast to the 2 bits per 2 dimensions we had for B. So in other words, there is a trade-off between your spectral efficiency and the minimum distance. We start with a k-dimensional Cartesian product of A, which has all points. We took a subset of points, and if we chose them smartly, we were able to increase the minimum distance, but the price we had to pay was to reduce the spectral efficiency.
Where did this 2/3 come from?
This 2 here?
2/3, yes.
Oh, 2/3, I am sending 2 bits per symbol, right? Each symbol has 3 dimensions. Okay, so it's 2/3 bit per dimension, or 4/3 bits per 2 dimensions. Okay, so the point was there seems like there is a trade-off between minimum distance and spectral efficiency. And indeed, this might seem like a reasonable trade-off, and a lot of coding theory that we will be seeing in the early part of the course is indeed motivated by this trade-off. You want to reduce your spectral efficiency in order to increase your probability of error. Okay. And this has in fact been quite a dominant design principle for a large number of codes that have come up in coding theory. However, if you look at what Shannon says something quite different. In Shannon's theorem, all they say is you have, if your spectral efficiency is below a certain amount, then your probability of bit error can be made arbitrarily small. Okay? So what Shannon is saying, it's something much stronger than this trade-off. He's saying if you reduce your spectral efficiency below a certain quantity, which is finite, then the probability of error can be made arbitrarily small. There is no statement of minimum distance in this theorem here. And indeed, if you look at the most modern codes which are capacity approaching, they are not designed to maximize the minimum distance. They are designed to work well with some practical decoding algorithms like the belief propagation algorithms and so on. So they are designed on a somewhat different principle than minimum distance. But nevertheless, this is quite a powerful tool that we'll be using in the early part of this course. We start with a k-dimensional Cartesian product, select a subset of points, and we want to increase minimum distance at the cost of spectral efficiency. Okay. Are there any questions?
This is just a binary decision.
That's a good question. Suppose I have a 2 p.m. constellation, then I can easily write the probability of bit error as a function of Q function. If it is a more complicated expression, I have to integrate over this decision regions, which we'll be seeing later on in this lecture. And it's not usually possible to get an exact probability of error expression. We usually use an union bound to bound it by a pairwise error probability. We'll be doing all that just now. So. Okay, so now I have talked enough about encoder, and we'll be visiting it very soon, but let us switch gears and talk about the decoder now. Okay, what does a decoder do? So the goal of a decoder is the following. You get your received vector y, which is x plus n, and from y you want to estimate x hat as a point in your signal constellation. So you receive a noisy version of x, and you want to estimate x hat at the decoder. So this is the architecture of your decoder, and the goal here is you want to minimize the probability of error. And what's the probability of error? It's basically probability that x is not equal to x hat. Okay, so that is your general criteria at the decoder. Now what we'll be doing next is basically going through this exercise to show that this minimum probability of error criteria is equivalent to a bunch of other criteria. So the first criteria is the map criteria, maximum a posteriori rule. So now our probability of error is basically, I can write it as an integral of probability of error given y times the density function of y So if I want to minimize my probability of error, I want to minimize each term in this integral. So this implies I want to minimize probability of error given y for each possible value of y. Okay. Now what's that going to be? Well, in order to look at what this term is, suppose I make a decision, right? I receive y and I decide a symbol aj is sent. Then what's the probability of error going to be? My probability of error given y is going to be 1 minus the probability that I was correct. Probability that I was correct is probability x equals aj given y. This is just follows from the definition. So if I want to minimize my probability of error given y, I want to naturally choose an aj that maximizes the probability of aj given y. So this implies choose aj and this is known as the map rule. So the idea behind the map rule is to choose the symbol in your constellation that maximizes the posterior probability given the received symbol. Now, this map rule is equivalent to the maximum likelihood rule under the assumption that all the signal points aj are equally likely. And the proof is not hard. You just use Bayes' theorem for that. So suppose all aj's are equally likely, then probability of aj given y, which by Bayes' theorem is the density of y given aj times the probability of aj, but since all the aj's are equally likely, I will just write it as 1 over m over the density of y. Okay. Now, because y is fixed, the density of y is fixed. So this quantity is just proportional to, it's a proportionality symbol, to the density of y given aj. I won't be writing all the vectors, I might be missing some, but please bear with me. So this implies we want to choose aj that maximizes the density of y given aj, and this is known as the maximum likelihood rule. And there is one final rule. Basically, if the noise is additive Gaussian, then the density of y given aj is simply proportional to e raised to minus the norm of y minus aj square. So if we want to maximize this quantity, we want to minimize y minus aj square. So we want to choose aj that minimizes the Euclidean distance between y minus aj, and this is known as the minimum distance decision rule, MDD rule. Yes? We are ignoring py because for a given y, py is going to be fixed for all possible choices of aj. The goal is I'm given y and I want to decide which signal point was sent. Because that's the probability of error given y. Right? This is my criteria now. So y is fixed. So the density of y is fixed. It's basically given by, in order to find this density, we'll just condition it on aj and sum up over all possible values of aj. It's like the marginal of y, right? I mean, to write this explicitly, I'm writing it here. It's going to be sigma p of y given aj times p of probability of aj. And this you can find by the conditional, by the Gaussian.
But then you have P of y given aj in the numerator as well as denominator.
But this is a summation over all possible aj's. I should write, sorry, aj's. This is just a summation over all k's, right? So basically, py is going to be a mixture of several Gaussians. Okay, and it's fixed.
Depending on your particular case.
Right. Okay. So we want to choose the minimum distance decision rule. And I should have the variance of noise here. Okay, so what we have so far is we started with the minimum probability of error rule. That's the criteria of your decoder. We showed this is equivalent to map rule. And that basically comes just from the definition. If you want to, in this integral here, we want to minimize each term in the integral. And that basically implies that the maximum a posterior rule is the best. This implied maximum likelihood rule. And maximum likelihood rule comes from the fact that all the signal points are equally likely. And this implies then the minimum distance decision rule. And that comes from the fact that your noise is additive Gaussian. So you have an exponential in the, you have the Euclidean distance as an exponent, and you want to minimize the Euclidean distance. So this is the story we have so far. And so it turns out that the minimum distance decision rule is actually quite nice because it gives you a lot of geometrical insights. So say I have 3 points. Let me not even draw the coordinates. My constellation A has 3 points. And let me write them as A1, A2, A3. This is my constellation, for example. And say I receive a symbol Y. Then the job of the decoder is to figure out whether I sent A1, A2, or A3. How will the decoder do that? Well, it will measure the distance from all the 3 constellation points and select the one with the smallest Euclidean distance. More generally, what we want to do is we want to look at the space of all received Y symbols and partition it into decision regions. So that if the point falls in a certain decision region, we say that the constellation point corresponding to that decision region was sent. Okay, and how do I find the decision regions? Well, I start drawing hyperplanes between every 2 pair of constellation points. Say I want to find the decision region of point A1. I draw a hyperplane between A1 and A3, which is given by this line. I draw a hyperplane between A1 and A2, which is given by this point. And so the region, the set of points which are closer to A1 than A2 and A3 is basically bounded by this region here. So this is my R1. Similarly, if I want to find a decision region for A2 and A3, I will draw this line here. This will be R2, and this will be R3. So these are my decision regions. So if I want to write that formally, Rj is my decision region, and it is the set of points Y belong to Rn such that the norm of Y minus Aj square is going to be less than or equal to. It doesn't matter if you have less than or equal to, because the point will lie in boundary with probability 0. That's Aj square. Okay, that's just the definition of Rj. Now, the way to construct Rj was to look at all the half planes which are closer to this point than any other point and take the intersection of all the half planes. So in other words, I can also write Rj to be the intersection of these half planes. The intersection is over all points j prime not equal to j of Rj j prime. So Rj j prime is your half plane where so norm of y minus aj prime square is greater than or equal to norm of y minus aj square. Okay. Note that this is aj prime and this is aj here. Okay. So it turns out that this decision regions have a somewhat nice structure because they are intersection of bunch of half planes. their shape is a convex polytope. And they are also known as by the name Voronoi regions. Okay, so these regions are known as Voronoi regions here. Now the set of points whose hyperplanes are active in a certain decision region has a special name to it, and it's called the relevant subset. So in this case, the relevant subset of A1 is A2 and A3 because both of them have hyperplanes that are active in the decision region of A1. So let me write that down. So that's the relevant subset is the set of points Aj prime whose hyperplanes are active in this decision region Rj. There's a theorem which says that the nearest neighbors are always included in the relevant subset. It's asserted in your notes. Okay. So now that we have this minimum distance decision rule, let us see how if we can get a hang over the probability of error. Okay. Let me see the probability of error given that I sent a symbol Aj. If I want to evaluate that probability of error, that's simply the probability that y does not belong to Rj given that I sent the symbol Aj. That's when an error happens. That's same as probability that the noise vector, because y is Aj plus n now, does not belong to Rj minus Aj. And the noise is independent of Aj, so I removed the conditioning. And that is 1 minus probability that the noise does belong to Rj minus Aj. If I want to find this integral, if I find this expression, I will integrate over the region Rj minus Aj of the conditional of the density of the noise dn. Now note that the noise has a spherical symmetry, but unfortunately, despite that, the integral is not a straightforward integral because this region here has sharp edges. The decision region is a convex polytope, so it's typically something like this. And if this was your point Aj, your noise does have a spherical symmetry about these spheres, but when it intersects the decision boundary, things get ugly. And so this is not a nice integral in general. And so unfortunately, there is not much progress we can make beyond this point for the exact probability of error expression. But we can say some nice geometrical properties about the probability of error. The first property is that probability of error is invariant to translations and this should be quite obvious. You have say a constellation with 2 points here, and say I subtract off the mean, so I get a different constellation whose points are like this. This is my constellation A, and this is my constellation A prime. The probability of error will be same for the two constellations because the decision regions will have the same distance from both the points. This should be quite obvious. And basically what this really says is if I have any constellation, I can always subtract off the mean and get another constellation with the same probability of error but with smaller average energy. And so this implies that any optimal constellation will have zero mean. The second point is the probability of error is invariant to orthonormal rotations. So if I had, say, one constellation with these 4 points, and I rotate it by 45 degrees, what I get is another constellation with these 4 points. And both these constellations are simply rotations of one another, and they have the same probability of error. And the easiest way to see that is the decision regions here are simply the 4 quadrants. And if I want to integrate my probability of error, I will be integrating it over this region. Here my decision regions will be these 45-degree lines. And if I want to integrate the probability of error for this point here, it will be given by noise which is symmetric about these circles. Basically, since the noise is invariant to orthonormal rotations, it should be quite obvious that the probability of error is invariant to rotations. Any rotation. Right.
So what do you mean by orthonormal rotation?
Basically, you are preserving the distance. So you're just rotating the point, not scaling it. Unitary rotation. Okay? I mean, you'll be proving this properties in the next homework, which is just handed out. Yes.
So the relation holds because minimum distance rule is orthonormal, right? And that's
right.
Because we assume Gaussian.
Because we assume Gaussian.
So that's the only assumption we need
Right.
for those things, right?
I think so. I mean,
Why the optimal constellation must have zero mean?
because if I have any constellation with a certain probability of error, right, I can always subtract out the mean from that constellation. I get a new constellation with a smaller average energy with the same probability of error. So,
So in terms of energy.
right, if you're looking at a trade-off of probability of error versus the energy, which is usually what we look at. So maybe that's a good point. I should just mention it there. Mean for probability of error versus if you're looking at this trade-off here. Okay. The next idea is to basically bound the probability of error by a union bound, because we cannot compute an exact expression for the probability of error, so we might as well compute a bound which is tractable. So we will look at what is known as the pairwise error probability. So the idea behind pairwise error probability is, suppose I send a point AJ, what is the probability that instead of AJ at the receiver, I decide that AJ prime was sent? This is the probability of, this is the pairwise error probability. So geometrically, if say AJ and AJ prime are 2 points here, let me draw some coordinate axis here. And when I say I send point AJ and there is noise on the channel, that takes me to this point. So this is my Y and this is the noise vector. Okay? And now what I want to know is under what conditions will I decide AJ prime over AJ, and what is the probability of deciding AJ prime over AJ. Okay, so let's draw a line joining AJ prime and AJ. So how would I decide? Suppose I receive this point Y and I wanted to decide between AJ and AJ prime. What would be my decision rule?
Take the distance.
You,
If the distance is smaller than AJ prime, then
you select
AJ
AJ prime.
prime.
Exactly. An equivalent way of saying it is to project Y onto this line AJ prime minus AJ. We take two projections, one orthogonal to the line, one along the line, and we see if this projection, hope this is a straight line like this. Let's call it N tilde. I should change my chalk. It's getting too blunt now. This distance is closer. This projection here is closer to AJ prime or AJ. So in other words, this probability of error is same as the probability that this N tilde, which is the projection of Y onto AJ prime minus AJ, is greater than or equal to the norm of AJ prime minus AJ over 2. Okay, now why did I use the notation N tilde here? Because the projection of Y onto AJ, which is this, N tilde is same as the projection of the noise onto the line joining AJ prime minus AJ. Okay, so N tilde, I can write it as the projection of N onto AJ prime minus AJ over the norm. Sorry?
Why is that?
Well, I mean, you can just see it geometrically, right? This is a 90 degree here. This is the noise. If I project the noise, it will be this component here. Oh, right, this should be 90. I'm sorry, this is 90. I'm messing things up. Okay, this is the noise here. This noise, if I project it onto AJ prime minus AJ, it's going to be this component. This is the Y. If I project it, it's the same component. Okay. Now, if the noise is IID with variance sigma square in each coordinate, we are simply projecting the noise onto one orthonormal vector. So N tilde is also Gaussian with zero mean variance sigma square. So we can use that to find this probability of error. So in that case, the probability of error, I should write this. Probability of AJ prime going to AJ is simply probability that this Gaussian is greater than some distance, and that's Q of norm of AJ prime minus AJ over 2 sigma. Yes. So the noise vector is IID in each of the components and has a variance of sigma square. Sigma is basically a naught over 2 if your noise is flat with, so let me just write that down, sigma square is a naught over 2. If you have an AWGN channel and you project it on each orthonormal signal, that's what you get. Okay.
When you project the noise vector on that line, variance and say you don't have.
So you have a noise vector. If you have a Gaussian vector and you project it onto an orthonormal basis.
Oh yes, but is this normal?
Right. And so H is this as unit. We are only projecting on one vector with unit norm.
you're saying, okay, yeah, the assumption is the noise is symmetric in all dimensions.
Right.
Yeah.
I mean, let's just do this again algebraically, so you are convinced that there is no magic I'm doing here. So we can write this as you said, is the probability that the norm of y minus aj square is greater than norm of y minus aj prime square, given that y I sent aj, so y is aj plus the noise vector. So I sub in for y, what I get is probability that y is aj plus n. So here I have norm of n square is greater than or equal to norm of aj plus n minus aj prime square. Okay. And since the only random variable here is this noise n, I can remove the conditioning as I have done there. Let me expand this second norm term there. That's basically the norm of aj minus aj prime square plus the norm of n square minus 2 times the projection of n, or rather the inner product of n and aj prime minus aj. So this is the probability that the inner product of n and aj prime minus aj is greater than or equal to norm of aj prime minus aj square over 2. If you divide by the norm of aj prime minus aj, you get the same expression as we had. Okay, so it's the same thing, and this was done geometrically, this is done algebraically. So this is the expression of the probability of error, and this is Q of the norm of aj prime minus aj over 2 sigma. Okay. So now that we have the pairwise error probability, we can use it to bound the probability of error given aj. Well, by definition, the probability of error given aj is simply the probability of the union of all possible error events of the type aj goes to aj prime over all possible j prime not equal to j. This by the union bound is less than or equal to the summations of the probability that aj goes to aj prime. That's just using union bound. And now I can sub that expression over from there. This is the same as so the summation is over j prime not equal to j times q of the norm of aj prime minus aj over 2 sigma. Okay. Now let me write the summation in a different way. I'm going to write the summation over all possible distances which belong to the set of distance times kd of aj times q of d over 2 sigma, where the set d is the set of all possible distances from aj Okay, and KD of AJ is the number of points at distance D from AJ. Okay, that's just a straightforward change of variables. Now, if you look at this expression, then Q of D over 2 sigma basically behaves like an exponential for large values of the argument. So recall that Q of x is like half e to the minus x square over 2 for x much larger than 1. And so what you are really seeing here is that you have a sum of a bunch of exponentials, each weighted by this term KD of HA. Now, if you think about the argument being large, then when you have a sum of exponentials, the term with the smallest exponent will dominate, because they are all decreasing exponentials. So this term can be written as approximately K min of AJ times Q of D min over 2 sigma. So what I'm doing is I'm only picking up one term in this from this summation. So far we have a strict upper bound here. So this summation is a strict upper bound on the probability of error given AJ. But now what I'm doing is I'm only going to keep one term in the summation, the term which has the smallest exponent here. So I'm looking at the D with the smallest the smallest value of D in this set of possible distances from HA. You're looking at essentially the nearest neighbor, geometrically speaking. And this approximation actually works quite well in practice. It's not a bound on the probability of error given AJ, but it's an approximation. And why did I do this? Well, if I want to look at the probability of overall error, what's that going to be? It's going to be the average over all possible AJs of probability of error given HA. Now, so I want to take an average of this quantity. So this is a constant. So I will just take the average over this. And that's going to be K min of the constellation, which is the average number of nearest neighbors, times Q of D min over 2 sigma. So this is approximate here. So this is an approximation that we will be used, and it's a very useful approximation, and it is known as the union bound estimate. It's no longer a bound on the probability of error, it's an estimate. And in fact, there is a homework problem where we will be showing that the union bound estimate is in fact exact for an MPAM constellation. Okay? And I will let you think why that is the case. I was going to do it, but then I realized it's a homework problem, so you might as well spend some time on it. So the last thing that I wanted to do today is find a lower bound on the probability of error. So if I look at probability of error, it's a union of bunch of the events. Yes.
On the first line at the top,
Right.
that union should be with AJ prime, right?
The union should be with AJ. It's not. Yeah. Isn't that what I have? So I'm taking a union over all possible events where AJ is confused to AJ prime.
Wouldn't it be AJ going to union J prime not equal to J, AJ prime?
Oh, I see.
I think you need
Yeah,
parentheses
the
around that.
brackets around the
After
AJ
the
going to
union
AJ.
symbol, there's another set of parentheses defining the event AJ going to AJ prime. Because that's the event you were talking about there. So I guess that's.
you're saying that
Just put parentheses after the U.
after the U, like this.
Yeah, right. And
Yeah.
that's the event.
Right, that's what I meant.
Right.
Okay, fine, fair enough. Okay. Okay, so basically the lower bound is actually quite simple. All I'm going to do is only take one event from that union. I'm only going to take one point, which is the minimum distance from AJ. Right? So probability of error given AJ is greater than or equal to probability that AJ goes to AJ prime, where now AJ prime is the nearest neighbor of AJ. And this we know from the PAM analysis is simply Q of d min over 2 sigma. So this is a strict lower bound on the probability of error, and it has the same exponent as the union bound estimate. Okay, so of course, I can, if I want to find the overall probability of error, I can just take an average of this. Since this is fixed, it's going to be the same quantity. So that's the lower. So what we saw so far, what we have is a union bound, a strict upper bound on the probability of error, which is this quantity here, a union bound estimate, and we have a lower bound on the probability of error. In the next lecture, we will be looking at how to use these bounds to compute a probability of error for small signal constellations and quantify the performance trade-off of the probability of error versus the EBNO, and so on. I think this is a natural point to stop. It's almost time now.